Yes, you are.
Okay.
Welcome, everyone, to the International Seminar on Automorphic Forms. Today, we have the pleasure of having Martí Roset Julià from McGill University, and he will tell us about rigid classes for SLN and their values at special points. Martí.
So first of all, thank you very much for the invitation to speak. And thanks to all of you for being here. And I'm going to speak on some joint work in progress with Peter Su. It aims to construct these so-called rigid classes for SLN and study their values at special points attached to totally real fields. So the main motivation for this work is it departs from the fact that the theory of complex multiplication implies that the CM values of modular units belong to abelian extensions of imaginary quadratic fields. And our main dream would be to try to generalize this statement to other type of number fields, and in particular, in this case, to totally real fields. So what I'm going to do is I'm going to start by recalling this classical story. And for this, I'll introduce a particular type of modular units called Siegel units. And I'll explain its relation or how its values are related to abelian extensions of imaginary quadratic fields. And I will even explain how Siegel units are constructed or outline it. And this is because some of the constructions that we'll see later will be a bit parallel to the constructions of Siegel units. Sorry, I just realized maybe I need to accept to record the meeting, but I think I just did. Okay, so the construction of Siegel units departs from the following proposition. Let's take E an elliptic curve over some scheme S. And let's say that we take an auxiliary integer Z prime to 6. Then we have the next proposition, which says that there exists a unique function on this elliptic curve, which is regular everywhere except at the C torsion, satisfying two conditions. The first condition is that its divisor is precisely the C torsion minus C square, the zero section. And the second condition is that the function is invariant under push forward induced by multiplication by A. And this has to happen for every integer A prime to C. So the idea to prove this proposition is that this divisor appearing in condition 1, it's actually a principal divisor. And this is because it has degree 0, and if we take the sum of these points in an elliptic curve, it will be 0. So in particular, this implies the existence of a function that has this divisor, at least locally. But this function will only be well-defined up to a constant. And then this condition number 2 pins down the constant uniquely, giving us the desired uniqueness, or even the possibility to glue these functions together to get something global unique. And now our aim is to use this proposition to construct some modular functions. So what we're going to do is we're going to apply this proposition to a universal elliptic curve, and then pull back this function, the function that we get by applying this proposition on the universal elliptic curve, to get functions on the modular curve that will be certain invariant functions on the upper half plane. So we'll apply this proposition to a universal elliptic curve. And to simplify, I'll already take a power of a prime level, just for things we'll do later, p prime greater or equal than 3, and we'll take it to be coprime to C, and we consider a universal elliptic curve. So we take the upper half plane times an elliptic curve, and we mod out by the diagonal action of the principal congruent subgroup of level gamma p to the r. And then if we project to the first component, we'll see that since gamma p to the r acts freely on H, the fibers of this map are elliptic curves. So in particular, we can apply this proposition, and we get a function, theta e, on the elliptic curve minus the C torsion. And now, as I said, what we're going to do is we're going to pull back this function by a torsion section to get functions on the modular curve. And torsion sections will be indexed by certain vectors of the following form. So let's say that we have a vector v1 over p to the r, v2 over p to the r. Let's say different than 0 of order p to the r. Then we can define a section of this curve. And the way we do it is, so recall that a point in the universal elliptic curve corresponds to, a point on the modular curve corresponds to an elliptic curve together with the basis of the p to the r torsion. And what we'll do is we'll map this to a p to the r torsion point in the elliptic curve above it. And this p to the r torsion point will be a combination of these basis elements where the coefficients are given by our vector v. And observe that this section, since P and C are coprime, it will never touch the C torsion. So let me call it V. So then we can define a function that will be our single unit that I'll write by CGV. And this will be the pullback of our theta function. And this, since we don't touch the C torsion, this gives an invertible function on the modular curve. So this is a single unit. So this is the construction of single units that we will later see when we talk about Eisenstein classes, that it's quite parallel. And for us, it might be convenient to view this single unit as a function on the upper half plane invariant by this congruent subgroup gamma p to the r. And now we can finally state the theorem that will be relevant for us, which is that let's say that we take tau, a point in the upper half plane, which is a CM point. Attached to K, a quadratic imaginary field. So this, in very simple terms, we could just say that it means that if we take the field generated by tau, it's a quadratic extension of Q, which is imaginary. But maybe in more group theoretic terms, for us, it will be convenient to see this as saying that tau is stabilized by some subgroup of SL2Q isomorphic to the norm 1 elements of a quadratic imaginary field. So here I'm viewing SL2Q acting on the upper half plane just by Moebius transformations. And what we're saying is that this point tau has a large stabilizer. And the claim is that then if we take a single unit and evaluate it at tau, this number belongs to an abelian extension of K. And in particular, it is algebraic. So we're being able to produce elements in abelian extensions of this quadratic imaginary field by evaluating this single unit at suitable points. And our goal, as I said, would be to try to generalize this sort of theorem or have a similar style of theorem, but for totally real fields. And we don't really achieve it, but we have some sort of conjectural statement. And maybe at this point, I'll mention that in this particular case, this theorem can be proven using the theory of complex multiplication in a very algebraic way. And the key is that both the construction of this theta function and therefore of these Siegel units can be made purely algebraically. And this gives functions that are defined over Q. And on the other hand, a CM point attached to K will correspond to an elliptic curve with complex multiplication by K together with the basis of the P to the R torsion. But the theory of complex multiplications tells us that such points are defined over abelian extensions of K, and therefore so is this value. So we would like to generalize this. This is our ideal motivation, to generalize it. To total real. But this aim doesn't come out of nowhere. But for example, the case of real quadratic fields has been extensively studied by several people. And now I'm going to explain an approach that was initiated by Henri Darmon and Samit Dasgupta that uses p-adic methods. And then this approach has been followed by several other people, and in particular by Darmon, Pozzi, and Bonk. So, and we're going to call this section logarithmic derivatives of Siegel units and real quadratic fields. So let's say that we have every real quadratic field. Then maybe the first thing, if we want to generalize this theorem, is to see how many ingredients of the previous theorem we could use for the setting of real quadratic fields. But we first very fast get to some problem, which is that the upper half plane has no real quadratic points. So setting this group theoretic way, there are no points tau in the upper half plane stabilized by some group in SL2Q, some subgroup of SL2Q, isomorphic to the norm one elements of a real quadratic field. And this is simply because if we take a point in P1C that had such stabilizer, then it would generate a real quadratic field, and it would have to be in the real line. But as we know, the upper half plane excludes precisely this. But the observation that has been quite useful in for many applications, not only for this one, is that there are actually geodesics that are stabilized by such subgroups. So there exist geodesics in H. In H, stabilized by such F1s. And for example, in this case, we could just take tau and its Galois conjugate and join this by a geodesic, and this path would actually have this subset would have a large stabilizer, precisely isomorphic to this group. And not only this, but we can extract interesting invariants out of this. So, moreover, if we take a segment of this geodesic, say from Z to gamma Z, a segment of the geodesic, so I'm taking here some Z, and then I'm acting on it by gamma, an element in the stabilizer of the geodesic. So I still land in the geodesic. And I'll even take gamma to be in one of these congruent subgroups that we considered before. Then what we can do is we can consider the integral of the logarithmic derivative of this same Siegel unit that we considered before from Z to gamma Z. And after normalizing it at 1 over 2 pi I, this is a zeta value of this real quadratic field, some partial zeta value attached to some Ray class group of conductor divisible by P to the R. So here I'll be a bit imprecise. And I'll just write, to remember, I'll just write P to the R. And okay. And this is the zeta value at 0. And note that these zeta functions, this is a zeta function, as I said, of some Ray class group. So in some sense, they contain information about some abelian extension, or these zeta functions contain information about some abelian extension attached to of this real quadratic field of certain conductor. So even though we cannot evaluate these single units, there's still some sort of information about abelian extensions of real quadratic fields in there, or at least that's what it seems. And now the other information to make is that these zeta values, as I said, they are integers and they satisfy very interesting p-adic properties. So for example, if you start replacing this number 0 by other non-positive integers, these values will still be integers and will satisfy interesting congruences, modulo powers of p. So if K1, if we evaluate that K1 and K2, and these K1 and K2 are highly congruent modulo power of p, these numbers, the zeta values will also be. And there's also interesting coherence among when you substitute when you put their different ideal classes. So I'll summarize this. I'll be a bit imprecise here, but I'll summarize this by saying that all these values where we vary the ideal classes, actually, including the R, we have to vary R, make R grow, can be used to construct a p-adic zeta function, or determine to construct a p-adic zeta function. Zeta function attached to the total real field, to the real quadratic field, sorry. And this will be some analytic function that interpolates some of these values. And the only thing to remember is that we would expect that such p-adic zeta function will contain interesting information about abelian extensions of it, or a given abelian extension of it. So at this point, I would say that the search of a symmetric space containing real quadratic irrationalities, together with the fact that we have access to these zeta values that behave nicely p-adically, is one of the things that motivated Darmon and Dasgupta to replace the upper half plane by a p-adic symmetric space, which is the p-adic upper half plane, and try to approach this question using this object. So the p-adic upper half plane, as a set, it looks very similar as the complex one. It's P1CP minus P1QP. So you can see it's very similar to the usual P1C minus P1R. And it also has a well-behaved theory of analytic functions that are called rigid analytic functions. And for us, the two main properties that we need to remember about the p-adic upper half plane are the following ones. So the first one, as I hinted, is that it has real quadratic points. So there exists tau in HP. I'll just write it in group theoretic terms. So stabilized by some norm one elements of the real quadratic field we took. So again, we have an action of Moebius transformations on HP. And there will be taus stabilized with large stabilizer isomorphic to the norm one elements of a real quadratic field, even only if P is non-split in F, which this can certainly happen for many primes. And this is actually, the reason for that is that if we have a point tau that, let's say that it belongs in P1CP and it has a stabilizer isomorphic to F1, the norm one elements of a real quadratic field, this point tau will see that it will generate such a real quadratic field. And this point tau will be in HP only if this real quadratic field is not contained in QP. And this is equivalent to saying that P has to be non-split in F. So you can see that this reasoning is very analogous to the reasoning one does to see which quadratic points we have in the upper half plane. But the role of the prime P there is replaced by the role of the prime infinity. And then the second thing, which is a bit more technical, and it's just to give a bit of an idea, is that thanks to the combinatorial nature of the p-adic numbers, it is possible to show that the ring of the multiplicative, the units of the functions on HP modulo constants, this is isomorphic to a space of measures in P1QP that have total mass 0. And if you have seen p-adic zeta functions or p-adical functions, you'll remember that to construct them, one usually constructs measures on spaces very similar than these ones. So what I want to say with this one is that I want to convince you somehow that this makes this space of functions on the p-adic upper half plane suitable to encode information about p-adic zeta functions, or even refinements of them. So I know this is a bit imprecise, but I wanted to give the idea about how one of the features of HP is that we have the possibility of, thanks to this isomorphism, to encode information about p-adic zeta functions. And we know that these objects should encode interesting arithmetic information. So now I'll summarize what is the main result of the recent works of Darmon, Pozzi, and Bonk. And I'll be a bit imprecise, but feel free to ask questions if something is unclear. So the first step of their work is a construction of what is called the rigid analytic class. So I'll write it by saying that what they do is these periods of these logarithmics of single units. So I'll say the quantities in star package into an object, it's called J, which is a cohomology class for SL2Z with values in A star. So the first step of their work is a construction of an object of this sort. They even construct something a bit more refined, but for the aim of this talk, this will be enough. And we have to think of this J as some sort of analog of the single unit. And then the second thing they do is they explain what it means to evaluate this class at a real quadratic point. So now let's take tau in HP, stabilized by some F1. In SL2Q. And let's look at its stabilizer inside SL2Z. So the idea is that this stabilizer will be something discrete inside F1, and that will be some sort of integral. So you have to think that this will be like the group of global units. So it will be generated by one element, essentially. And then what they do is they define what it means to evaluate this rigid class at tau. So this rigid class is a cohomology class for SL2Z with values in A star. So let's take a representative that I'll write with the same symbol. Then we evaluate it at the stabilizer of tau. This gives us an element in A star. And then we evaluate this function at tau. And this gives a number. And their theorem is that a priori this number could be a p-adic number, even in CP star, or in the completion of F at P. But their claim is that this element actually belongs to an abelian extension of F. So we like to see this theorem as some generalization of the theorem we saw before about that the values of single units at CM point belong to abelian extensions of the field attached to this. So J can be seen as a generalization of this single unit CGV. And the difference is that what we did is we replaced and before we had some H0, namely invariant functions, and now we replace it by some H1. As well as we replace an Archimedean space by a non-Archimedean space. But this, another thing that you could see as analogy is that an H0 quadratic imaginary fields have global units of rank 0, while real quadratic fields have global units of rank 1. So this might indicate some hints also about these degrees of cohomology. And I'll say one last thing about their work, which will connect a bit what I was saying at the start about zeta values, which is that their theorem, the theorem above, refines the following formula that can also be proved. So one could take this value j of tau and apply some norm of it. I'll be a bit imprecise, but one can, this j tau actually belongs to the completion of f at p, and one can apply the norm, and then the p-adic logarithm. And it's possible to prove that this is equal to a derivative of a p-adic zeta function attached to some ideal class at 0. So you can see that this formula has a type of formula as star conjectures. It's actually in the style of what is called the gross star conjecture. And then the expectation of this conjecture, which is in fact proven, is that this number here should be some unit in an abelian extension. And this is what it's proven in more detail, like if we saw the full statement in Darmon Potzibong. So the result is some sort of refinement of this equation together with some gross star conjecture. Okay. Of course, if there's any questions at any point, feel free to say it. Because now we'll move to the next point, which would be that what we would like to do is we would like to generalize or have a possible statement of this theorem, but for totally real fields. And as we saw, it seemed that single units and their logarithmic derivatives played an important role in both constructions. So then the thing that we'll try to do is to find an analog of these logarithmic derivatives of single units, but that contains information about totally real fields. And the analog that we'll try to study is what is called the Eisen-class torus bound. So these classes have been studied by several people, and already they found applications in similar directions than the one I'll explain. So for example, Beilinson, Kings, and Levin, also Galanakis and Spies, and also Bergeron, Pierre, and Luis are here. And I'll focus precisely in this approach by Bergeron, Sarla, and Garcia, as it seems quite suitable or quite similar to some of the things I explained. So now let's take n greater or equal than 2. This will indicate, for example, the degree of the fields that we will study. And the role of the upper half plane will be played by the symmetric space of SLNR that will denote by x infinity. And again, we'll also consider quotients of these bicongruent subgroups. So let me take r greater or equal than 1, VR to be a vector whose first entry is 1 over p to the r, and the remaining 0 in Qn mod Cn. and let gamma R be its stabilizer. So I'm doing this to define some congruent subgroups in SLN. So this gamma R is some analog of the congruent subgroup gamma 1 of P to the R. So it's the first entry has to be 1 and the remaining have to be 0 mod P. And the rest, it can be IC. And now the construction that I'm going to do will look very similar to what we did in the first point. So first, the role of the universal elliptic curve will be played by what is called the torus bundle. So consider the torus bundle that will write by TR. And what we do is we take x infinity times an n torus, and we mod out by the diagonal action of gamma R. And then we project this into the first component. So if the action of gamma R in x infinity was free, then we would see that the fibers of this map would be n torus. And this is why we put the name torus bundle. Here, this is not entirely correct. This gamma R has torsion, but this can be fixed either by intersecting gamma R by another congruent subgroup that is torsion-free, or by working in the world of equivariant cohomology. But for the aim of this presentation, we'll just suppose that this is a torus bundle, as nothing will change. That nothing doesn't really change. But here there's some small technical detail. But you see that this object, when n is 2, it's really some real analytic version of the universal elliptic curve. The difference is precisely this, that as soon as we grow with n, these objects don't have a complex structure anymore. So we might not be as lucky to be able to construct some functions or holomorphic functions that behaves nicely. And we'll have to content ourselves with constructing some cohomology classes, singular cohomology classes. So what we do is we take this combination of torsion points, the C torsion minus C to the n, the 0 section. And we can view this as a class in H0 of the C torsion, right? Because a class in H0 would be determined by a map from the C torsion to Z. And this is just the identity map, and this is just the identity on the 0 section and 0 everywhere else. And now we have to use something that it's called a Thom isomorphism to interpret this class in H0 of the C torsion as a class in Hn of TR and TR minus the C torsion, relative to TR minus the C torsion. So this is what it's called the Thom isomorphism. So the idea of this isomorphism, maybe I can give you the map in the opposite direction. The idea to understand it is to view TR as a bundle. We can think of it for a moment as a bundle over the C torsion, or just if you're not convinced, just think that the C torsion is just the 0 section in this case. And whenever we have a form, an N form in this relative cohomology, what we can do is we can integrate it over the fibers. And when we integrate it over the fibers, we'll get something in the base. That in this case it would be like the C torsion. And in the process of doing so, we'll have decreased the degree of the form by the dimension of the fibers, which is precisely n. So that's how we're considering a class in Hn, that when we apply this process to go to the base by integration over the fibers, it gives us this combination of torsion sections. And now we consider the following long exact sequence. In relative cohomology, attached to this pair, TR and TR minus the C torsion. So it goes like this. We have Hn minus 1 of TR, Hn minus 1 of TR minus the C torsion, Hn of the relative cohomology and Hn of Tr. And then I'm going to denote this connecting morphism by delta. And observe that this class here, we have it in this relative cohomology group. And we can finally state the theorem that you'll see that will look very similar to the theorem that we used to construct theta functions. So this theorem, the first part is due to Sullivan, and it was later refined by Bergeron, Charola, and Garcia. And I'll state their version here. So sorry. So what the theorem states is that there is a unique class CZR in Hn minus 1 of Tr minus the C torsion after inverting C, satisfying two conditions. The first condition is that the image of this class by the connecting morphism, delta, is equal to the, is equal to TRC minus C to the n, the zero section. And the second property is that this class is invariant under push forward induced by multiplication by A. For every A prime to C. So you can see that this theorem looks very much as the proposition that we saw at the start. And in fact, so if we took n equals to 2, this class CZR would be related, very related, to the logarithmic derivative of these theta functions. Maybe with 1 over 2. And the idea being that, remember that this function here had precisely divisor E of C minus C squared 0. And this is what would force that when we apply this connecting morphism here, we would get precisely this class. So this is a generalization. And now we have our analog of the theta function. And what we want to do is we want to produce our analog of the Siegel units. So we're going to pull back these functions by a torsion section. So again, the vector VR induces a torsion section. So from x infinity mod gamma r to TR. And again, since P and C are coprime, this doesn't touch the C torsion. So we can consider the pullback. And this gives us a class in Hn minus 1 on x infinity mod gamma r with values in C1 over C. And this is our analog of a Siegel unit. And again, just as in the case of Siegel units, we have this property that the periods of this class encode information about partial zeta values, but now of totally real fields. So the periods of this class encode partial zeta values of totally real fields. And therefore, we expect that it encodes some sort of information about the Abelian extensions of these fields. So now we have our analog of the logarithmic derivatives of Siegel units. And the idea is to now try to consider these pullbacks of Eisenstein classes, but not for only one P to the R torsion section, but for arbitrary large P to the R torsion sections. So make P and P grow, and hope that by considering more and more classes, we can construct out of them some invariants that are more refined than these zeta values. And the way we will package this is via these rigid classes. Rigid classes and their values. So now we want to find an analog of this theorem of the Darmon-Boggi bond, but just as a conjecture for now. So in this case, the role of the p-adic upper half plane is played by what is called the Drinfeld symmetric domain. So it's a higher dimensional generalization that, as I said, is Pn minus 1 Cp, where what we do is we erase all QP rational hyperplanes. So the idea is that the point in XP is a point in Pn minus 1 Cp that is represented by a vector whose coordinates are QP linearly independent. And again, this space has a well-behaved theory of analytic functions that will denote again the space of functions again by A. And now, so what we aim to do is to construct some rigid class. So I'll write it in a moment what will be, but so the summary of the construction. So it will be a class that will also denote by J, which will be now in degree n minus 1 for the group gamma, that remember that is SLNZ, with values in A star. That's the ideal statement. We want a cohomology class now in degree n minus 1 for gamma valued in functions of the Drinfeld symmetric space. The summary of the construction of J is the following. So what we do is we'll start with these pullbacks of Eisenstein classes. But as I said, we'll try to consider all p power torsion section pullbacks, or at least for arbitrary p to the r growing. And here, let's leave a space for a moment. So this will be these classes. We saw that they are classes in singular cohomology for X infinity mod gamma with coefficients in Z1 over C. And the key fact is that thanks to the uniqueness of the Eisenstein class and to this invariant under push forward induced by multiplication by A, in this case by multiplication by P, this implies that these classes satisfy some distribution relations. And more precisely, what it means is that they are compatible with respect to push forward by the quotient map from X infinity mod gamma r to X infinity mod gamma r minus 1. So all these classes packaged together. So this is the starting object. And let me say that already these compatibility properties, for example, imply a lot of properties about partials at the values of totally real fields. And this has been used to construct to construct the p-adic zeta function of this totally real field, for example. And this is essentially where most of the information will come. Then when we have this, the next step, what we do is we package all this information in a group cocycle. And more precisely, this is what it's called an Eisenstein cocycle. So this is a class in Hn-1, but now a cohomology group class for gamma, SLMC, and valid in some space of measures of mass 0 on a simple p-adic space. That it is Zp to the n minus PZP to the n. So it's try to package all these classes together into a group cocycle and valid on measures on this space. And finally, the last step is to go from here to our desired class. Now I'll give a bit of details of each of the steps. So this second step is again because there are some relations between measures on these p-adic spaces that look a bit simpler and functions on the dreamfall symmetric space. So this is step one and this is step two. I'm being a bit imprecise, but I hope this gives a bit the idea. So now I'll try to say some words about each of the steps. The first step is essentially Shapiro's lemma. So the idea is that we start with these singular cohomology classes that I'll even put ZP coefficients. Remember that C is prime to P. And what we do is we go from singular cohomology to group cohomology for the groups gamma R. That remember that these gamma R are these congruent subgroups stabilizer of the R. And now we use Shapiro's lemma to get some compatible system of classes for the group gamma now valid in the index representation from gamma R to gamma. And now, so now this inverse limit is with respect to some maps in this index representation. And the idea is that this index representation from gamma R to gamma is somehow indexing maps from open sets in Y of a particular shape of the style a vector plus P to the R ZP. This is because the stabilizer of such open set and the stabilizer of VR are both equal to gamma R. And in this way, one can see that this inverse limit transforms into some sort of measure condition. And from there, one can move the inverse limit inside and get a class for gamma valid on measures on Y. And then there's still some work to make them of mass 0 and find the canonical lift. And then the second step is the use of what is called the kernel function. So here, I'll give a bit less explanation, but I'll write the formula for a moment. So the idea is that there is a map from measures on Y to ZP, two functions on A. And the way this map works is when you have a measure, you define a function that since X goes to the integral with respect to this measure of Y. So here the principle is somehow that this space Y is a bit related to the boundary of XP, and there's some sort of theory of kernel functions that says that when you have measures on the boundary, you can construct functions on the interior by integration. But the important thing is to know that there's some sort of maps from these spaces of measures to spaces of functions that they behave well under the action of gamma and allows us to go from cocycles valid on measures to cocycles valid on functions. So here I wrote something that it's not exactly A star, but there's, because I wrote an additive integral, but there's some multiplicative refinement to get this. Okay, so at this point, we have constructed, or I have outlined the constructed of this class. And what we did is we had these singular cohomology classes. We packaged them all together. We packaged them all together into a group cocycle valid on measures on this space Y. And then we went from measures to functions on dream field symmetric space. So now the next thing to do would be to understand interesting special points on this space XP and define what it would mean to evaluate the class J at the special point. So what I will do is I'll give some example of special points now. So for this, let's take F, a totally real field. Of degree n. And we need an important assumption, which is that we need to assume that P is inert. And attached to this field F, or now let's take a vector in F to the n, such that its coordinates give a Q basis of F. So my claim is that this point tau, this vector tau in F to the n, after viewing it in Pn minus 1 of Cp, it gives naturally a point in the dream field's p-adic symmetric domain. And the idea is precisely because since P is inert, the coordinates of tau will not only be Q linearly independent, but will be QP linearly independent, because the degree of the completion of F over QP is also n. So tau gives a point in XP, and this point is special. It is a special point in the sense that it has a large stabilizer. And it precisely, it is stabilized by some group isomorphic to the norm 1 elements of F inside SLN. So this is our candidate of special points where we want to evaluate our cocycle. And the way we do this is to observe that then, here one needs sometimes some more conditions on tau, but that's the idea, is that then we can, let's suppose, but there are certainly a lot of cases, that the stabilizer of tau inside SL and Z. So what will happen is that this stabilizer, again, will be something like the units on the field F, the global units in the field F. So this will be isomorphic to some subgroup of the global units of F. And in particular, inside here, we can take, for example, the totally positive units. That by the Dirichlet unit theorem will have that they will be isomorphic to Z to the n minus 1. So now recall, we have our class J, that is a class in Hn minus 1 of gamma valid in A star. And we have our point tau that has a large stabilizer. And inside the stabilizer, we have a group isomorphic to Z to the n minus 1. So it looks that we're in good shape to try to define an evaluation between these two objects. So what we do is we define the value of J at tau. So we take our class J, we evaluate it at tau. So this would give us a class in Hn minus 1 of the stabilizer of tau valid in Cp star. And on the other hand, we have that this group OF plus star is isomorphic to Z to the n minus 1. So we can cap it with the fundamental class, a generator of this group. That would be in H lower n minus 1. And this will give an invariant. And by the definitions, one can check that this invariant belongs to F star, but it's still a p-adic number. And now the question is whether we can give some interpretation to these values, some arithmetic interpretation. So I'll start saying the result that we have. So what we have is that if we take this number, let's say that the summary is that we have that some sort of average of these numbers is an average of an algebraic number in the abelian extension that we would expect. So we have that if we take the norm of this number and then we apply the p-adic logarithm, then this is equal to the p-adic logarithm of the norm, what it's called the gross start unit for u tau in something like an abelian extension of f. Here I'm a bit imprecise. Sometimes one has to tensor by q, say, take something like the global units tensor q, but that's the idea. And at this point, then, it is very tempting to try to hope whether one actually have the equality between j tau and u tau without these norms. And this would recover the theorem of Darmon-Pot-Zinfong, but in more generality. So it raises the following question. And I would say that this question is essentially motivated by the works when n equals to 2, but also by the works of Dasgupta and Kagde, that they have some constructions of these elements here, some proven constructions of these elements. And we feel that our constructions have somehow similar, they use similar ingredients and satisfy similar properties that made us hope that maybe there's hope for this question to be true. So do we have the logarithm of j tau is equal to the logarithm of u tau for u tau in f abelian? So this would be the ideal thing that we would like to prove. And maybe I will conclude by saying a very small word about the proof of this theorem. So which is that the idea to prove this theorem, the theorem is to, on one hand, there is this formula. So what we can relate this number to the derivative of a p-adic zeta function attached to a totally real field. And then there is the important gross star conjecture proved by Darmon, Dasgupta, and Pollack that says that this is proven, this is equal to the norm of a unit. And this gross star conjecture, the proof is quite interesting because it connects these invariants to Fourier coefficients of p-adic families of modular forms. And from there, it connects p-adic families of modular forms to Galois representations. And the arithmetic of these invariants come from the arithmetic of Galois representations. So it gives a proof that it's quite different than the original proofs that we saw, for example, to prove algebraicity of CM values of Siegel units. So I will end here. Thank you very much for your attention.
Thank you very much, Martí, for a wonderful talk. Let's all thank Martí. And we can, Ricardo, can you please stop the recording?